There's an enzyme inside the COVID virus that has been making antivirals less effective since 2020. Yesterday, a team in Iowa published the first atomic resolution map of how it does it. In the same news cycle, a 6-country African consortium published the first year of decentralized malaria genomic surveillance. Clinic laptops, sequencing samples for under $25. A Hong Kong materials team published a new stainless steel that survives inside a seawater electrolyzer. And the European Commission walked into a press briefing and confirmed it's in preview access talks with a frontier AI lab over a cyber model. Let me walk you through it today. Here's the first problem. When you take an antiviral for COVID, it works through molecular sabotage. The drug looks like one of the building blocks the virus uses to copy its own RNA. The virus's replication machinery grabs that lookalike, slots it into the copy, and it ruins the copy. Remdesivir works this way. So do the other antivirals. Coronaviruses do something almost no other RNA virus does. They proofread. There's an enzyme called exoribonuclease that runs along behind the copying machine. It scans the new RNA, it finds the bad nucleotide that the drug snuck in, and it cuts it out. The sabotage gets thrown away. That single proofreading function is the biggest reason that remdesivir works less effectively against SARS-CoV-2 than similar drugs work against viruses that don't proofread. For 6 years, antiviral chemists have known that the proofreader was the problem, and they have not been able to see it clearly enough to design around it. Earlier images of the enzyme were too blurry to map which atoms were doing the recognition work. But a team at Iowa State, led by Yang, published 2 papers yesterday in Nature Communications and PNAS with images of this enzyme at 2.4 angstroms. That's a new record for this particular enzyme. At that scale, you can see exactly which functional groups touch which, exactly where the modified nucleotides sit, and exactly the shape the enzyme is recognizing as flawed. 2 design pathways open from there. 1, redesign the antiviral so that the bad RNA it generates carries a shape that the proofreader doesn't recognize, so the proofreader simply walks past it and the sabotage stays in. Or 2, design a separate drug that binds the proofreader itself, locks it shut, and increases its grip on the modified RNA so that it grabs the bad material and refuses to release it. Either path needed the geometry that Yang's team just produced. What I want you to notice underneath this: the Cryo EM hardware hasn't changed dramatically in the last few years. What changed is sample preparation, the protocols. The team developed new methods, tested them at their home facility, ran the final imaging at one of the 3 federally funded Cryo EM centers in the country, compounding improvements on hardware that was already capable, better tools, better therapeutic surface. If you had COVID and you remember what the antivirals could and couldn't do, the next generation of those drugs is being designed against geometry that was invisible until yesterday. And the same imaging protocols apply to every other RNA virus that will eventually be in the field at this scale: flu, hepatitis, and the next coronavirus, whenever it happens to come along. All right, switching hemispheres here. A consortium of African research institutions published a paper in Nature Communications yesterday describing 1 year of decentralized malaria genomic surveillance across 6 sub-Saharan countries. 1,065 samples sequenced locally, on laptops, in clinics. Costs under $25 per sample, roughly a 5-hour turnaround. The results display on an offline dashboard that you can run on a machine with intermittent internet. The why: malaria kills more than 500,000 people a year in sub-Saharan Africa. The parasite is evolving in 2 specific directions that threaten the region's defenses. First, mutations in a gene called Kelch13 are making the artemisinin combination therapies clear parasites more slowly, and in some combinations, they simply fail outright. And second, deletions in 2 genes called HRP2 and HRP3 are producing parasites that simply don't show up on the rapid diagnostic tests that most clinics use, so you get false negatives. People walk home untreated. Both threats spread fastest where surveillance is thinnest, and until this protocol, surveillance meant shipping samples across continents to centralized labs in Europe or North America. Months of round trip. The parasite was moving faster than the data, so the architecture flipped. The same buildings where patients are treated now have the equipment to read the parasite. African scientists, African samples, African epidemiological decisions. The data flows into a regional picture managed by the institutions producing it. The team estimates real continental coverage needs about 50 to 100,000 samples a year. They sequenced 1,065 in year one. So what I want you to see here is what changed from there. A piece of hardware that used to need a humidity-controlled core facility now runs in a clinic with spotty Wi-Fi. A protocol that used to need a PhD-staffed lab now runs in 5 hours on a laptop. A diagnostic decision that used to wait for a sample to travel 6,000 miles and come back now happens before the patient even leaves. The system being assembled is a public health nervous system that runs at the speed pathogens actually move. And the platform is general. The same sequencing rig, the same offline dashboard, the same training pipeline that lets a clinic identify a Kelch13 mutation in 5 hours can, in principle, track tuberculosis resistance, viral outbreaks, zoonotic spillovers as they emerge. The same architecture is positioned to catch the next epidemic earlier than the last one did. All right, switching domains again, from biology to chemistry. A University of Hong Kong team led by Mingxin Huang published yesterday in Materials Today a new stainless steel called SSH. Why anyone should care? This alloy survives the inside of a seawater electrolyzer. Here's the 2-minute primer. Green hydrogen is the dream of splitting water into hydrogen and oxygen using clean electricity. The cleanest, cheapest version of that would split seawater directly. You don't need to desalinate first. You don't need freshwater inputs. And the world has rather a lot of seawater. The problem is that seawater is corrosive. Salty water at the voltages required to split it eats most metals, including stainless steel. The chromium oxide film that protects ordinary stainless steel breaks down at around 1,000 millivolts in chloride environments. The reaction that you need for water splitting requires about 1,600 millivolts. Above 1,000, the chromium simply dissolves. Your electrolyzer turns into salt soup. That gap is the reason that every industrial seawater electrolyzer built so far uses titanium components plated with platinum or gold. Titanium because it survives, platinum because it accelerates the reaction. Both are scarce and both are expensive, so the economics never quite worked. SSH2 closes the gap through what the team calls dual passivation. The familiar chromium oxide film forms first, above about 720 millivolts. A second protective layer based on manganese oxide forms on top of the chromium layer. That manganese layer keeps protecting the metal through the entire water splitting window, up to 1,700 millivolts, well above what the chemistry needs. What's strange about this is that the manganese has long been treated as a corrosion liability in stainless steel chemistry. The researchers said it took them several years of atomic level work before they themselves accepted what they were seeing. The liability was actually the protection. Stainless steel is one of the most manufactured materials on Earth. Titanium plated with precious metals is one of the least scalable. A Hong Kong team published the paper yesterday on a new stainless steel that survives inside of a seawater electrolyzer at 1,700 millivolts, the voltage that green hydrogen needs. The cost arithmetic here: structural materials in a 10 megawatt electrolyzer drop by roughly a factor of 40. 40 times cheaper than the titanium and platinum path. The chemistry that the green hydrogen economy had been waiting for is now sitting in a paper through a passivation mechanism the field had treated as a corrosion liability for decades. The number sits inside a single engineering study, and it will need independent validation under real operating conditions. The order of magnitude is the signal, though. If the alloy holds up in deployment, the substrate underneath industrial hydrogen rearranges. So if you have a kid in school today and you've ever wondered what their world's energy system is actually going to look like, papers like this one are where it gets built. A common alloy meeting an electrochemical bar that locked the entire industry into expensive alternatives. A reasonable read of this is that the cost stack of cheap hydrogen gets cheaper, and the expensive path keeps getting harder to justify on its own terms. All right, last story for today. This one is institutional. The European Commission held a press briefing yesterday. Spokesperson Thomas Regnier confirmed two things. First, OpenAI is in active preview access discussions with the EU over GPT-5.5 Cyber, the cybersecurity variant of its frontier models that started rolling out to vetted defenders earlier this month. An initial framework already exists between OpenAI and the Commission. More discussions are scheduled for this week. Regnier's stated purpose: follow deployment of the model very closely and address security concerns. Second confirmation, Anthropic and the EU are also talking about Mythos, Anthropic's restructured cyber model, but Regnier said that those talks are at a different stage. Anthropic has not yet granted EU regulators preview access. A month after restricted release, Brussels still hasn't seen Mythos. Two background facts to anchor this. The April 16th edition of the Century Report covered structural divergence between OpenAI's and Anthropic's release strategies. And on May 2nd, the UK AI Security Institute published benchmark results showing that GPT 5.5 matched Mythos preview on advanced cyber capability at 71.4% versus 68.6% on expert capture the flag, and 3 out of 10 versus 2 out of 10 on the hardest evaluation. The technical asymmetry that the opposite release postures were built on is in public reporting now. What is genuinely new yesterday is the jurisdictional layer landing on top of those technical conditions. The EU is the first major regulator outside the US and the UK to engage either lab on a concrete preview pathway for a too dangerous to release cyber model. Two labs entering EU regulatory talks on opposite footings in public, with the Commission setting the cadence. The architecture that this dissolves is the one in place for the last 5 years. Frontier capability release has run on a discretionary access architecture. A handful of labs decided which defenders inside which jurisdictions got to see the models first. The assumption within that was that the company was the gatekeeper for a capability shaping cyber defense across financial systems in Frankfurt, energy systems in Lyon, and telecoms in Helsinki. Bilateral relationships between a lab and a few select major power regulators were treated as a sufficient review function for the rest of the world. That assumption met something it can't accommodate at Regnier's press briefing. Stitch it together with the Five Eyes Joint Agentic AI Guidance, the Bank of England's emergency coordination, the IMF's spring meetings forcing labs to talk to finance ministries, and what comes into focus is a multi-continent verification layer being built for frontier cyber capability. Out of conditions a single lab's release decision can no longer contain. If you have money in a pension fund or a bank or an insurer, then your money sits inside the infrastructure that those institutions are responsible for defending. The cyber capability landing in defender hands inside the EU was, until yesterday, going to land through whatever bilateral channels OpenAI and Anthropic chose to open. That all changed in a press briefing. The running record on this lives in the ARC tracker on the website if you want to check it out. Okay, so to close for today. In one frame, we see a viral enzyme that has held against 6 years of antiviral chemistry, yielding its geometry at 2.4 angstroms. A continental-scale pathogen surveillance system that needed centralized labs on 2 other continents now runs on a clinic laptop for $25 a sample. A scarce alloy chemistry that locked seawater hydrogen to platinum coatings got replaced by a common stainless steel through a passivation mechanism the field had treated as a liability for decades. And a single lab discretionary release architecture for the most dangerous cyber capability the labs have produced started getting reviewed by a regulator no lab is going to get to set terms with. In each one, the thing that was named as the bottleneck stopped being the bottleneck. What I want you to take from this, if you've absorbed for years the idea that the big problems are intractable because of some fundamental constraint somebody named, the constraint is almost always the inventory of tools at a particular moment. The tools change. The verdict follows. The toolkit underneath medicine and energy and AI governance is compounding fast enough that the limits being named today are mostly limits being named on the basis of yesterday's equipment. Deployment timelines still matter, months to years, between a Nature Communications paper and a patient sitting in an oncology appointment with a new prescription. If you live somewhere downstream of a regulator that hadn't, until yesterday, gotten access to a frontier cyber model, the access pathway is being built now, not 5 years from now. If you have an electricity bill or a job touched by green hydrogen economics, or a kid who's going to grow up in the energy system that gets built next, the substrate under all of it is being reformulated in papers being published this week. What to watch here in the near future: a non-malaria pathogen run through the African nanopore protocol, tuberculosis, an outbreak, a zoonotic spillover, an independent industrial electrolyzer validation of SSH2, a jurisdiction outside the EU entering preview access talks for a frontier cyber model. Because once one of those happens, others probably follow. What looked like a wall yesterday is often just a door whose key the field hadn't learned to cut. Several keys got cut yesterday. We'll see you tomorrow.